Morning.
Good
Good morning.
morning. Okay, so welcome for the second day session of Stata. I'm just saying that still some people are entering, so I'll wait for maybe 1 minute. In the meantime, I think all of you who have already joined, I was wondering if you could download the training material that's given in the chat. I can show you in the chat. I think SciExpert has given the link, and I hope that all of you already downloaded. And what I try to keep in that, I can show you my screen. I'm sorry, I didn't share my screen yet. So let me share my screen. Okay, so you will get all the information, I think, in this drive, data driven decision making. I gave the, what you say, PowerPoint and the do file also. The do file I'll not be using because all the codes are already in the slide. So I'll be showing you by copying and pasting in the console of Stata. Okay. Now I can minimize my slide and then start my slides. I can see some chat, hopefully. It's still possible to access the folder from Monday session to find there the presentation with the comments. I think I have uploaded the file. And I mean, if you go to the same folder that you have access already, Monday's folder, there are 3 files. Let me show you. Sorry. Okay, let me show you my folders. So I think I gave you both on, this was the Monday session. So when you go to Monday session, the first one I uploaded without comment, I think, and then because of the request, I did with the comment. And today's section, sorry, in today's sections, I did not have a separate slide for me, and whatever comment I made, I have uploaded the same thing that I'm going to use today. And there is do file that you can use for the future reference, but all the course already in the slide. Let me see. I confirm that the presentation with comments available. Yes, Elena, thank you so much. And is there. Thank you. So because again, time is too limited and the topics was covered was too vast. At least I think that one topic could be taught even for a whole day. So, and from 3 hours, the teaching hours is just 2.5 hours. So it's going to be a little bit intense. But if you have question during the session, you can raise your hand and ask, or if I'm explaining something and I can't answer your question that moment, you can write the question in the chat that I can, during the break time, I will try to answer your questions. Okay, the today's link unfortunately does not allow me to move another folder. Sorry for bothering. Um, I'm not able to attend the session on Monday. Could I please give me the access to folder? Richard, I think you need to talk to expert because they are the people who is conducting and they have the sole ownership of my material. So the yes, mm, let me see. Okay, let me put both the folder for you here so that. Stata, let me give you the my Stata 26 link. So yeah, I mean June 26, that's our both the sessions. I'm giving the link and anyone with that link can access this and done. So I will give in the chat again for both days things. And this training sessions are recorded, so expert will also place all these videos in each folder. Like Monday's video will be in Monday's folder, and today's one will be into a video will be into today's session. Okay, so let's start instead of asking so much question now. Okay. Mm. Yeah, I think we can start. At final, can we receive a participation certificate? I think yes, but still that's not my responsibility. That should be expert's responsibility, and they do give the participation certificate for the course. Okay, now that's all. I'm not taking any more question because it's going to be too late. So let me start with the presentation now. Okay, so good morning all for the second day session, and it's about data-driven decision making with Stata. And here we are going to cover a bit advanced topics actually for research, business, and public policy. And some of you, I think, have joined the day one training, or even this is, I think, my ninth or 10th session with expert on Stata, though I have covered the different topic like for survival analysis, econometrics, or Stata basics, different things. So this time I'm taking this advanced one only for the econometrics. And about me, my name is Sabiha Gulshan. At the moment, I'm working as a data analyst in Link Shopping University. I also work as a freelance data analyst on Upwork platform. And about my educational background, I have done my bachelor's and master's in statistics first, and then also I did another master's in demography from Stockholm University. So that's all about me. Let's start today's session. So what's our target audience for this course, especially public sector analysts or policymakers, business analysts or commercial professionals, applied econometrics, data analysts, and consultants. And the prerequisite, as I said, that this is a bit advanced level course. So basic statistics and regression concept is required to understand, otherwise it's going to be hard. As I'll not be explaining two basic things because I can't cover with the time frame then. And also it's expected that you have familiarity with the Stata fundamentals, like how to open Stata, how to load data set, how to open a do file, and these basic things, because I can't cover that again in these short sessions. Sorry. I can see again some chats are coming. Yes, okay, this is from expert addressing some of your question, that the recording will be shared and it will be in the I think, I'm not sure how they are going to send. Either they're going to send you the link or it will be placed in this June 26 Stata training folder in the Google Drive. So you will have access to it. And another things that at the end of this slide, you will see my contact email address, and also you have Sci Experts contact address, so you can reach them even after the session if you have any question about the thing that we are going to learn today. And during the session, you can ask me question, you can raise your raise your hand, and if I allow you, grant you access, then you can ask the question. Otherwise, if you see that I'm not noticing that you are raising your hand or you wanted to talk, then you can put in the chat your question that I will address at the end of the session, or during the break time. We have break from 10:30 to 11. Okay. So what is expected from this session? By the end of this training, actually, you should be able to understand and address endogeneity using instrumental variable and also two-stage least square methods, conduct advanced time series forecasting using ARIMA and VAR models, applying causal inference method for policy and impact evaluation, estimate and interpret the dynamic panel models, and use machine learning tools such as Lasso for predicting and model selection, and create analytical output or support evidence-based decision making, and develop reproducible analytical workflows in Stata. So again, you can see from these terms or from these learning outcomes is quite advanced topics. And within this 2.5 hours training, definitely we won't be able to go so much deep, but it can be just starting point for you. So we have structured the session into 3 parts. From 9 to 10:30, we'll be learning about advanced econometric modeling, and then we'll take a break from 10:30 to 11, and we'll start session 2 at 11 to 12. And you can in session 2, we'll be trying to do some more advanced analytics such as ARIMA forecasting, difference in difference, Lasso, and so on. So let's start with session 1, when we are going to talk about endogeneity, IV, 2SLS, dynamic panel, and GM. So let's start from here. I tried to make it about the data things, to use as few data set as possible, because if I keep on changing the data set and then I have to give you explanation of the data set, that takes time. So throughout the session 1, I'll be using this data. But in the second session, I think we are using 2 more data set that I will explain later on. So here our data set comes. I think yesterday also not yesterday, on Monday's session, I also used the same data set for some analysis. So this data set comes from National Longitudinal Survey of Young Women, and it includes 28,535 34 observations for the women aged 14 to 24 in 1968. And these are the variable of interest. But before, instead that I keep on talking about the data set, let us look at the data set from Stata. So that's going to be our first Stata command. I hope all of you have that data Stata open here. Okay. As I said, that I also uploaded the do file, that what we are going to do everything. But I'm not running my do file, but you can use it as for your future reference. I can see could you please send the link of the presentation? Um, I have just sent it. Okay. Okay, 1 second. Yeah, because if you don't have access, it's going to be hard. So before I start, make sure that everyone has this. So Stata Training and then copy link. Okay, I think someone has done, as I also copied, so it's here. Thank you. Um, so about the data set, we are going to do our first code. So let's explore the data set a bit. As I said, let's see what does this data set include. So here you can see the variables and the label of the variables, but for the better visuality, I already included in my slide. You can see that what are the variables of interest, or the data set include the variable with the describe command or des command, whatever you like. So we can see here these are the variable. This is ID variable, and then interview year, birth year, age, and all these things. But for our interest, actually, we will be using log ln os here. You can say ln os. That's nothing but natural logarithm of the of os. And the grade is the years of education, as you know it. Tenure is the years of current employer. Union, whether the participant has joined the union membership or not, and race, ID code, and the year is the survey year. And we can also see here, as I included in the description, that there are total 28,534 observation, and the data include the information about young women aged 14 to 24 years old in 1968. So that's the brief description of dataset. You can also get a better idea about the dataset from summarize command that shows the details for each variable, the number of observation, mean, standard deviation, minimum and maximum values. If you would like to see, I mean, before starting analysis, always good idea to explore your data set or know your data set, so you know exactly what you are going to do and what is possible to do from this data set. So here you can see, have a look at the data set. Okay, all those variables that we have. Now, as we have idea about the data set, now we can move forward with the other part. Move forward. Now, here you might be asking that we have OLS, we learned OLS in our day one training, and then why do we need advanced econometric methods? So the justification is OLS performs very well when explanatory variables are exogenous, meaning that they are uncorrelated with the error term. But in practice, however, uh, in the real world scenario, this assumption is often violated. We may have the endogeneity, that means omitted variable. We can face also reverse causality and have the measurement error, or deal with the selection and dynamic process biases. Okay, under this situation, OLS estimates can become biased and may not be representative, represent the causal effect. These challenges motivate the use of more advanced economic methods. So, estimating the causal effect of education, we are now going to explore the with the example, for example, how to estimate the causal effect of education on wages. Uh, so far, I don't see any question in the chat, so I'll move forward. Sorry. Now, with our same data set, this NLS work data set, that we are going to explore the research question, does the education increase women wages? So what happens? We just need to see that if we run this OLS, I wrote here naive because in this case, it will not capture the things that we want to do it. So now let's run first our OLS method and then see what happens and why OLS cannot be always the right choice. So I'm going to run the OLS and see what happens. So when we run this OLS and to explore the research question, does education increase women wages? Here, what our OLS result shows, the log uh, n, the coefficient 0.90 on the grade, that is nothing but, and also we'll look at the p-value, and this is statistically significant, yeah, and it means that additional year of education is associated with approximately 9% higher wages and highly statistical significant. And we also look at the model here, R square, here 0.1932. So the model only explains 19% variation of the data. And the problem here with this OLS output, yeah, before we conclude about this education causes wages to rise 9%, we should ask whether the education is truly exogenous. Consider the unobserved factors here. Unobserved factors here. More able individuals may complete more years of education, and the same ability may make more productive or therefore earn higher wages because the ability is not observed, so it becomes part of the error term. Consequently, education becomes correlated with so what happens, the education becomes correlated with the error term and violates the key assumption of OLS. In this case, the estimated 9%, percent return to education may be capturing not only the effect of education itself, but it also affects the unobserved ability. This problem is known as endogeneity, and it is one of the main reasons economists use the advanced econometric methods such as instrumental variables. Okay, so we move this. This was just justification that why not OLS and what happens and what is the solution for this. We're going to move forward. Now, we mentioned that we have just seen that endogeneity can make OLS estimate biased. One possible solution is to use instrumental variable. But what is instrumental variable? An instrumental is an external variable, for example, Z, here in this case, we can give a name Z, uh, a variable that influence the endogenous variable X or do not directly affect the outcome variable and is unrelated to an observed factor in the error term. So in our example, education can be our education is endogenous because unobserved ability affect both the education and wages. So one possible instrument that we can use here, distance to the nearest college. Okay, uh, with thinking or justification that individuals living closer to the college may be more likely to pursue further education simply because access is easier. Okay, and importantly, the distance itself cannot distance itself should not directly determine the wages. Its effect on wages should operate only through education. So, for an instrument to be valued, uh, it must satisfy two conditions. One is relevance. It must be correlated with education. The second condition that it must satisfy is exogeneity. It must be unrelated to unobserved factors such as ability, cognitive skill, and so on, that also affect the wages. So if these assumptions are hold, then instrumental variables allow us to estimate the causal effect of the education and education on wages. So with having this, let's move to a bit more theory here. Once we have a valid instrument, we can estimate the model using two-stage least square or 2SLS in short. In the first stage, what we do, we use the instrument here, Z is the instrument to predict education. Here, grade is our education variable. So we predict the education. Okay. The predicted education contains only the variation explained by the instrument and is therefore less contaminated by unobserved ability. In the second stage, what we are going to do is we replace the instrumental we replace the actual education with the predicted education and estimate the ways of ways education. Okay. The resulting coefficient coefficient measures the, so what would happen after these two stages? Actually, in the stage one, will I isolate the variation in education unrelated to ability, and stage two estimates the causal effect of education on wages, and the coefficient beta 1 I'm sorry, beta they interpret as the IV estimate of the return to the education. So let's move forward in looking at some codes, because you are in the stata training, not in the theory training, but this small I mean, Stata will do its good job to find those measures, but uh, to interpret the result from the IV or 2S LS estimation in Stata, you need to know the basic theory behind this. So here we now estimate the instrumental variable model using two-stage least square. So here we already have uploaded our data. I always include the data set before any uh, command, but you can ignore that. You don't need to use that here, and you can run the two-stage least square model. So you can copy directly from here. I mean, I'll copy all of this and explain all together the output. Okay. So here the key findings, we go here. This is our IV variable, 2LS regression model. The coefficient on grade we can see is 2.29 and the p-value is 0.0. I mean, it's less than, and the interpretation can be one additional year of education is associated with approximately 29% higher wages. And we can see and the instrument relevance here, the we can move here. First stage regression summary statistics. You can see here that I don't know why. Yeah, it's 547.37 almost, and which is much higher than 10, and it shows that instrument is very strong. So to explain in more details, here the coefficients for, I'm sorry, I'm going back here. The coefficients for the age and the tenure are also statistically significant. Tenure has a positive effect association with the wages, while the age has negative, small negative coefficient after controlling for education and nature. Next, we examine whether our instrument is sufficiently strong or not. And for that, check this F statistics, uh, which is approximately 547, which is substantially larger than the common rule of thumb threshold is 10. So this is much higher than 10. This suggests that the instrument is strongly correlated with education and does not suffer from the weak instrument problem. Finally, we examine the endogeneity with this one test. Both the here both the Darwin and Husam test produces p-value smaller than 0. I mean, p-value is extremely small. Therefore, we reject the null hypothesis that education is exogenous. This provides statistical evidence that treating education as an endogenous variable is appropriate, and it supports the use of instrumental variable estimation rather than relying solely on ordinary least square methods. This is important to remember that in this example, south we used in our IV command. We can go back here. Sorry. Yeah, south here. The example south is used primarily to demonstrate the IV workflow in Stata. And in applied research, the credibility of an instrument must be always justified theoretically and carefully evaluated. Again, I would like to give little more explanation about our IV model here. I'm sorry. Okay, so in this model, uh, 2SLS model, you estimates both the stages automatically. Inside the parenthesis here, Stata treats grade as endogenous and uses south as an instrument. After estimation, then we go for estat command here, first stage, and tell us whether the instrument is strongly predicts education or not, while the next command for us that we have done is stat endogenous, test whether the OLS is inconsistent because the education is endogenous. So that's all for now, this IV and methods. Now that this is little bit again theory, and it could be the similar concept I'm going to emphasize to understand the interpretation or the mechanism behind those instrument variable. So finding a valid instrument is often the most difficult part of IB analysis. And remember that a valid instrument must satisfy two conditions. I already, I think, mentioned it, but I would like to do into more details. So because it requires two conditions to satisfy. What is our first condition? It must be relevant, meaning that it has a strong relationship with the endogenous variable. We often assess this using the first F statistics that we just have seen now in the previous slide, where a value above 10 is commonly used as a rule of thumb. And the second condition that it must satisfy is the instrument must be exogenous, meaning that it affects the outcome only through the endogenous variable and is not correlated with unobserved factors in the error term. While statistical tests can help, economic theory and subject matter knowledge remain the essential for defined instrumental validity. Okay. So what is the common problem here with the 2SLS model or instrument variable that is weak instrument can lead to biased and imprecise IV estimates, and also invalid instrument can give inconsistent and misleading causal reference. So we need to be careful with that. So that's all about our first topic, I can say. We're moving to the next, dynamic panel models, like when past outcomes influence the current outcomes. So let's see here. The key question is, why do we need dynamic panel models? So with using the same data set and keeping the research question in our mind, do past wage influence the current wages? So here, many economic outcomes exhibit persistence over time. And in labor market, especially, a worker current wage may depend partly on what she earned in the previous period, and in addition to her education, job tenure, and age. To study this, we use again the same data set, NLS W panel data set, and estimate the dynamic model. With this is the model, dynamic model equation. You can say, just you don't need to know it, but because Stata will do that its job with the command, but you can just have a look. Let's do this with the stata. In stata, we first, as you know, that we first declared the panel structure using XT set ID code and year ID, and the year is the time variable. So this is our data set, and it's already uploaded, so you don't need to do it. This is just kind of repetition, but this is very important, that XT set and ID code to declare the data is in panel Oh, sorry. So why do we run this code here? In Stata, we declare the panel structure using the XDset, then this code. Then estimate the model using Arellano or Arellano bond estimator. And this is the model, this one, Arellano bond estimator regression. But before that, I mean, when you run this code directly, some of you might get error that this is not installed. So you have to install only once. I already have done it, but for you who is, I mean, running this, don't have the installation, so you can do and install it. But I'm not going to do it because or if I do also, not, no harm is there, but you should do only once. But this is for me taking time because this is second time I have already installed. Okay, so now let's do our Arellano bond estimator and see that what happens after we run this model. Okay, so here our key findings. So we look at the key findings here. The lagged ways here, the coefficient is 0.78, suggesting that some persistence in the ways over time, although the estimate is only marginally statistically significant. Here, I'm sorry, I can see a mistake in my note because maybe I was in hurry while copying or typing. So it should be p-value is 0.088, actually not 78. 78 is our coefficient. So p-value is 0.88, which is marginally statistically significant, not uh, at the 10% level. And education and tenure, this is our education and the tenure coefficients, and the age, we can see that they are statistical positive and statistically significant effects. They have statistically significant effects on wages. For example, how can we interpret this grade 0.72 is 73 or whatever, an additional year of schooling associated with approximately 7.3 higher wages, while an additional year of tenure and additional year of age is associated about 1.7% and 2.2% higher wage respectively. We do not simply estimate. Now, you might be thinking that why not use FE model with the lagged logarithm of ways. So we do not simply estimate the fixed effect model with the lag dependent variable because the lagged ways variable becomes correlated with the unbiased individual effects, producing something called a nickel bias. And the Arellano bond estimator addresses this problem by using internal instrument based on lagged values of the dependent variable, allowing to obtain the more consistent estimate of this dynamic relation. So now we are in the next slide, we are going to check, because now I have given you the theory that, oh, if I mean, why we shouldn't use FE or which is better, but now with the stata code we are going to check that in the next slide. Okay, So here, to justify that, why can't we simply use FE? Suppose that we simply estimate the fixed effect model and include the lagged wages as a regressor. We obtain a coefficient, but before that, let me run these two codes, the fixed effect model code. Already the data set is declared as panel structure, so you can ignore maybe the first code, but you can run the model directly. I'm doing both. So this is our coefficients. Let's see that what this coefficient meant to us. So when we run the FE model, the coefficient is about 0.41, suggesting that the current ways, and this is statistically significant, current ways depend heavily on the past wages. However, in dynamic panel settings, the lag dependent variable is correlated with the unobserved individual effect, creating what we call as nickel bias. Therefore, the FE estimate can be biased upward. We then estimate the Arellano bond model using the X band, the same thing that we did before, but we are going to run this model to have a comparison. So the estimate here presents here the estimate, you can see the coefficients also even from here. The estimated persistence coefficients fall substantially to 0.08, 0.08, and it's only marginally statistically significant, just like we saw the before also at 10%. And this suggests that the waste persistent exists but is much weaker once we account for the dynamic panel bias. Another advantage that our Arellano bond allows us to estimate the effects of education, tenure, and age. We find that here we can see the estimates from here. We find that additional year of schooling sorry. Okay, additional year of schooling is associated with roughly 7.3% higher wage, while the tenure and is positively related to the wage as well. And this same thing we have already explained, I think, in the previous slide, so I'm not going to go into deeper. So what main lesson this teach us this slide or from here to take away is that when the current outcomes depend on the past outcome, standard FE estimators can be misleading. And dynamic panel estimators such as the Arellano bond provide more reliable estimates. So let's move now to the next slide, and where we want to address that how does the Arellano bond GMM work? What's the mechanism behind it? So we have seen that the including a lag dependent variable in a fixed effect model creates nickel bias because the last year's is correlated with unobserved individual characteristics such as ability and motivation. To address this problem, actually, we use Arellano bond generalized method of moment, or in short, we say GMM estimator. In Stata, we first declared the panel structure that already we have done that. So we have this is our data set and XD set ID and the time variable. It declares the data is in panel data structure, and then we are going to set our model with XT-band plan. So the key advantage of the key advantage of this estimator is that it generates internal instrument for data itself according to the output. Stata uses here GMM type lagged to this of the variable. And this means that the second and the deeper lag lag deeper lags of wages, such as you can say lag for the previous, like 2 months before or 3 months before, and so on, and used as instrument for the last year's wage, like lag T1, I mean the last year's. Yeah, the intuition is that the earlier wages are still informative about the year's wage, so they have predictive power, but they are less likely to be correlated with today's error term. Therefore, they can help isolate the exogenous variation in the lag dependent variable. So let's run this. Already we have run this code, and we are going to see what our result says. Here we can see our results such that there is some wage persistence over time. The coefficient on the lagged wage variable is approximately 0.78, and again our p-value is 0.88, so indicating that higher wages in the previous period are associated with higher wage today, although this effect is only marginally statistically significant at 10% level. We also find the education tenure and age has have positive and statistically significant effect on wages. And I'm not including all this explanation, because this is just nothing but repetition. So what the main takeaway for this Arellano bond GMM allows us to estimate dynamic relationship more consistently by replacing the problematic lagged dependent variable with a valid internal instrument derived from its deeper lag. So think of GMM as just letting the data instrument itself. We use older values of wages to help estimate the effect of recent wages of current wages. Okay, now let's move to the next one. Again, here in this slide, I included the mechanism behind the difference GMM. The name, it's difference GMM, actually comes from from the first step of estimator. We first take the differences of the model, and then which removes all the all the time invariant characteristic of individuals, such as innate ability, motivation, and work ethics. And however, the difference alone does not solve the problem completely. The difference lag dependent variable remains correlated with the difference error term, and therefore we need instrument here. And or Arellano bond uses deeper lags of this dependent variable, such as the wages from two or more periods ago, and as internal instrument. This earlier wages are informative about the last year's wage, but are less likely to be correlated with today's shock. So in Stata, this happens automatically. I mean, we don't need those. Stata doesn't need all this theory, but we to interpret the model, we need the mechanism how it works. So in Stata, this happens automatically when we estimate the model with the X band, and the output already we explained that it reports the GM type lag 2 or indicating the second and deeper lag of the wages are being used for the instrument. The key intuition is the simple difference GMM. First remove the fixed individual characteristics and then uses deeper historical information in the data to deal with endogeneity arising from the lag dependent variable. The key idea here of Arellano bond is simpler. After removing the individual effects by differencing, we use older values of dependent variable as internal instruments to break the correlation between the lagged outcomes and the error terms. Now, we are moving to system GMM to improve the difference GMM. Now, in the previous section, we have learned that difference GMM removes individual effects and uses lagged levels as instrument. However, when variables are highly persistent, such as wages, those lagged levels can become a weak instrument, making the estimator less efficient. So what's the solution? The solution, one of the solution can be, or improvement of the difference of GMM is the system GMM, which addresses this limitation by estimating two equations simultaneously. I didn't include here, two equation here simultaneously, a difference equation and a level equation, difference equation and the level equation here. It also introduced additional moment conditions and the instrument. Now, as a result, system GMM generally produces stronger instrument and perform the better in short panel with many individuals and relatively few time periods. Since the wages tend to become persistent over time, system GMM can often provide more efficient estimates than difference GMM. So you might be now wondering where do the additional instrument come from? The answer is the system GMM uses lagged levels of instruments for difference equation and lag differences and instrument level equation. So let's explore a bit more. So here we estimate this is we are going to do with Stata, the system GMM estimation in Stata. So here we estimate the system GMM using the user written command X. This is the command. I'm sorry. This is the command. Again, just like before we did it, you need to um, use the same data set we are using. You need to declare the data set as a panel data structure that we have done. And if you don't, if you haven't installed this XTA bond 2, then the model will not run. So for that purpose, you have to do, but run only once. You don't need to run many times. If you install the software or install this XTA band 2 multiple times, no harm in that, but it's just waste of time. Okay, so now let's run our model. I can copy all of them here. We don't need to include that. It takes a while to come because I have run the many codes at a time. Okay. So here we estimate the system GM model using the user written command XTA bond 2. The command estimates the dynamic Weiss equation in which the current Weiss depend on the previous Weiss. Education tenure, education tenure, and the age. And what the parameters or the output says, let's explore the output here. We can see the persistent parameter on lagged wages is approximately 0.434 and highly statistically significant. This indicates substantial wage persistence. Workers with higher wages in the previous period tend to have higher wages in the current period as well. And we also can see the education, tenure, and age all remains the important determinant of the ways for education, that 1 year additional schooling is associated with approximately 4.9% increase in ways. Tenure, we can say, and age also have the positive and statistically significant effects, as it has extremely low p-value. We can say that we also examine that the several diagnostic tests with this command, because you can see that with the model I have included GMM and a lot of other things, so that two-step robust, so that we can do some diagnostic test. It's now when we go down, what we see here, Orellano bond test for AR1, the first difference Z is 9.5. So I already have the, you need to here look at the p-value is 0. So less than, this is less than 0.01, which is expected in fast differences. However, the significant here, A2, also has very low p-value. This is also significant. That this specification may still have issue related to serial correlation instrumental validity. Therefore, we should treat here, we should treat this as an illustrative example of system GMM estimation rather than a final empirical specification. In applied research model, model specification and instrument validity always require the careful evaluation. This is the something very fast. I think we have touched upon some very advanced topic, but it requires more theoretical understanding that when to use which model, and it depends on the diagnostic test also. So the key things about this one, we said that illustrative example only. In applied research, the model specification and instrument validity should be carefully evaluated. So far, I don't see any question. As I said, that if you have question, you can put that in the chat, and we can address that. Also, as I said, that I included all this in this. You can run the codes directly, or you can just keep for your future reference. And by this one, we have, I think I rushed a little bit, and I was a bit nervous that I will not be able to explain all this. So I finished the first part, uh, and if you don't have any question, then what I would do, because our second session is even shorter than this, the first session, we have only 1 hour, so I can push, I can move forward with the second session, and when it's exactly 10:30, then I stop and give you a break and complete the remaining material. Is that okay with you? If is that okay, just write okay in the chat and I can move forward. Otherwise, I can take the questions also. Okay. All right, great. So yes, I will push this break to little. So in the second session, which courses or material would you recommend for the learning basics data? I don't know whether you speak from the SI expert perspective, because I have taken, I think I have conducted two sessions initially when I started with SI expert about the basic. So you, if you would like to have the training from the SI expert, you can talk to them so that they can they can arrange to conduct another course for the basics of Stata, uh, that where I I mean, you don't need to have any kind of experience about Stata. I would show you, I have shown, or I will show in that course, if they are going to conduct, and that how to open Stata and what are the interface, and how to navigate through the different interface in Stata, and how to select your work directory, and how to open do file to save your work, and how to load the data set, how to save all your work actually in the log file also. So all the basic things will be given, how to create a data set, or how to upload or load data set in Stata from either from your device, or from your either from your device, or data also can be uploaded in different format like CSV file, and CSV file, or Excel file, or SPSS data set, or Stata data set. So that all will be covered only in the basic one. But this time, as our program is for bit advanced people, already they know, or they have maybe spent quite some time with Stata, and they would like to use for the research purpose. Okay, so I have taken the, yeah, someone asked for the things. Stata, I think link, yes, link is given, which course material, that's fine. Okay, if any more question about the different courses, let me know. As I already mentioned that from PsyExpert, this is my 9th or 10th session. So initially I used to conduct the basics and intermediate and advanced level of stata in general, but due to the different demand, we have moved or conducted also some session only exclusively for the econometrics modeling, and also I did for survival analysis or few months ago, and this time also based on the demand of PsyExpert, we have gone. But basically today's session is more focused on the econometrics modeling. Okay. Any more question? If no more question, let me start from the second session. Okay. So in the second session, we are dealing with forecasting. As I can see some question again. I think yes, you will receive a certificate of participation, and I think after you are done, then PsyExpert will be sending your participation, and if you did not receive, you can contact to the PsyExpert people in their email address is called info@psyexpert dot something. Any more question? No. Hopefully no. Another, I can see another question. We'll receive this. Okay, thank you. Thank you. All right. So in the session 2, we are going to deal with forecasting, causal inference, and the prediction. And what the application we are going to focus on today is the ARIMA forecasting, difference in difference, lasso, and decision support. So let's start again with the theory. I love to give the basic theory before I start and run the stata code, and because when we run the code and we get the code, but interpretation is very important, and to interpret those models or our findings, if you don't have the basic theory behind it, then it's hard to interpret. So in session 1, our main goal was causal inference, the understanding why outcome occurs. But in forecasting has different objective actually. Here we are less concerned about causality and more interested in predicting what is likely happen next. So examples can include forecasting airline passengers. These are some of this use. It's just some I have included. Definitely they are not, forecasting is not limited to these examples only. There is a huge use of forecasting. So forecasting, why do the organization need forecast? They need to anticipate the future trends, like especially for the business organization or the bank or the people where they would like to see the sales forecasting. That's very important one. And also allocate the resources efficiently and manage the uncertainty and support the planning and decision making. So what are the some application field of forecasting? As I said, that this is just some example, but it's not limited to that. It's a huge vast topic. So it can be used in business, for example, sales forecasting, demand planning, inventory management. For the public sector, it can be inflation forecasting, unemployment forecasting, or tax revenue forecasting, tax revenue projections. And in the research field, can be population projections, especially. I'm too interested in this sector because I'm a demographer. So we'd like to see the population projections, and as you know already, in the most of the countries, especially in a lot of European countries, the population is dying, population growth is reduced, declining. So that becomes very important for the policymakers, that what could be done. Economic trends, like also the scenario analysis, and so on. Uh, so if also we can consider about the research question, like can historical data be used to predict future outcomes? For example, future airline passengers, or future sales, future GDP growth, or future unemployment rate. So forecast here, the key idea is forecasting uses the historical pattern to make informed prediction about the future. Definitely we need to be prepared for the future, so we need to do our groundwork to be proactive rather than reactive, and forecasting help us for that. So that's little background about why forecasting matters. And let's move to the next slide. And here, in the first session, we tried to use one data set. And also here in this section, we are using most of the time, for most of the analysis, we used uh, airlines data set. This is also Stata inbuilt airline passenger dataset. Why I tried to include all the dataset from Stata inbuilt dataset, so that you don't need to take hassle to download the dataset, and also I don't want to go through this. There are some kind of um, privacy policy that I'm like, now I work with a lot of data set, but those data set I cannot share with anyone. So we will use status inbuilt airline passenger data set, which contains 144 monthly observation from the period 1949 to 1960. So before that, let us load our data set. I already mentioned in first session that when you use Stata inbuilt dataset, you can use web use and then dataset. And why are we writing clear? Clear means, I mean, whatever is in the memory, because now I have the previous dataset in Stata memory. So when you don't include clear, then Stata will give a command. So now let's see it, that if I don't include clear, what happens? Oh, it uses. Okay. So, but sometimes the data will give you that, okay, there is data set in the memory, so it cannot. I think we are already using this one. So anyway, now let us have some look at our data sets here. So this, there are only three variables: air, time, and t is the time variable. The first one, let's see, let's browse it. So if you use browse or br, then you should have a look at the data sets. So here it includes in the time the year, but this is the time variable that will be our interest, will be using it. And dataset characteristics, before we use this, we need to also use this command. uh, Okay, before I declare it, let me give you a brief description about our dataset. This dataset exhibits two important characteristics of many economic time series. A clear upward trend, we'll see it upward or not upward. Next slide with the visualization, and a strong seasonality. I don't know why I included all these notes here, but it should be in the next one. And passenger numbers are related to previous months. Okay, this comes in the next slide. So here, if we declare the data set, here what research question we are interested in: can historical passenger data be used to forecast future passenger demand? Now, why is this data set useful? Because this series exhibits the trend, seasonality, serial dependence that you will all see from the visualization in the next slide. But here just the theory, which makes it an excellent data set for the illustrating and forecasting method. And the last question is why we need to use ARIMA. So ARIMA models are designed to capture the trends and also autocorrelation and persistent in the previous observation. So keeping all this in the mind, we are moving to explore or to see the data set more in details in the next slide. So here, before building any forecasting model, our first step is always visualize the series, like what's happening. So to get an idea about the data series, here we are loading data set and declaring as a time series using TS set. So already we are done with these two parts. This is our data set, and then we have already declared that data set is in the time series format. And now we are going to make the visualization of the air, and let's see what we see. So I have included the same visualization here. I can do this. Yeah. So what we can see, looking at the graph, you need to look the key observation. When you look at this, what are the key observation here? We observe that a clear upward trend, and the airline passenger numbers generally increase over time. So when we look at this time period, it increase over time, indicating that the average level of series is not constant. So there is a variability. The second thing that we observe is very pronounced is the seasonal pattern. You can see there is up and down in every period. It goes to the peak and it goes down. Passenger numbers rise and fall in a fairly regular cycle, suggesting that the certain months consistently experience higher demand than others. The third thing that we notice that the fluctuation become larger as the time progress. Here we can see the fluctuation is smaller, but as the time proceed, it becomes higher. Okay. Um, Early in the series, the movement are relatively small, but later peaks and troughs become much more pronounced. This suggests that increasing variability over the time. And taken together, these features indicating that the series is likely non-stationary. Both, what does it mean by that? Both the mean and the variability appear to change over time. It's not static, but there is variability. It changes over time. This observation is extremely important because many time series models, including ARIMA, requires a stationary or at least some transformation towards stationary. Therefore, our next step is to formally examine whether the series is stationary and determine whether the transformations such as differencing are needed before fitting the forecasting model. So here we are going to ask, or the key question is, can we statistically verify that series in non-stationary in non-stationary? Or if so, how can we transform it into a form suitable for forecasting? So forecasting, you just cannot, it doesn't happen uh, uh, all of a sudden. It's a process. So here, the things we need to be careful, this pattern suggests that the raw series is unlikely to be stationary and may require transformation before ARIMA modeling. So we close this visualization now, and we see what we move to the next. Here again, before we move or set the ARIMA model, we need to understand some theory behind it, or understand what does this ARIMA model stands for. So what does ARIMA stand for? ARIMA has three-part components of ARIMA. I mean, the model itself is the auto-regressive integrated moving average. That's the abbreviation of this. And it has the three component. What is the first component? AR, autoregressive, which is nothing but current value depends on the past value. And I from integrated, this is nothing but differencing removes trend, helps achieve that stationary. And the last part is MA, is nothing but moving average. This is the current value depends on the past forecast errors. So I already said the three parts, and here when we look at this example of the ARIMA model, including 111. What in the ARIMA model, when we specify the ARIMA model, we choose actually three parameters, P, D, and Q. So first one, P, D, and Q. What does that P means? This represent P is the autoregressive term, and the next one, D, or the next term here will be the differences, and the last one is the moving average term. So for example, in this example, the model contains one autoregressive term and then one difference, which is our first differencing, and one moving average term. So the challenge in forecasting is determining the appropriate value of these parameters P, D, and Q before fitting an ARIMA model. We first need to determine whether the series is stationary. Okay, so as I already mentioned here, before fitting ARIMA model, we need to determine whether the time series is stationary. But now the question is, what is stationary? Okay, so a stationary series has statistical properties that remain relatively stable over time, including its mean, variance, and correlation structure. And now another question is, why does it matter? So here, the most forecasting model, including ARIMA, assumes stationarity. So if this condition is not satisfied, then we cannot use ARIMA model for the forecasting. Okay. So this is important because the most forecasting model assume that the underlying process is stable, and if the series exhibits strong trends or changing pattern over time, the model may produce unreliable forecasting. So when we consider the airline passenger data, then we are that we are using appears to show upward trend. Already we have seen here, it shows the upward trend. I'll go back here. Upward trend and recurring pattern. Again, we say that there is recurring pattern because there is some seasonality, variability in every time period. It goes up and it goes down. And The model may suggesting that it may not be stationary. One common solution is differencing then, where we are going to consider the differencing, where we examine the changes from one period, changes the period, like this is the present period, and the past period, the difference between these two periods. Examine the changes from one period to the next rather than the original level of the series. This process actually represented by integrated component of ARIMA, which is I in the ARIMA model. So in our ARIMA model, integrated this part. Okay. I don't know that because it's 10:30, if we should go for break and then when I come back and complete it, yes, because it will take bit time. So um, uh, or 1 second, let me check. Um, no, so it's better to go for break now because and follow the structure of the lesson now, and we can continue by 11 then. And if you have any question, you can write in the chat that I will try to answer. Okay. Okay, so welcome back, all of you. And I have seen only one question in the chat, so I answered it. And if still you need more clarification, let me know. Otherwise, we just continue where we have stopped. So let me share my screen. Okay. Okay. So can you see my slide, all of you? Say okay if because it yes, excellent. Thank you. Thank you. All right. So what so far we have covered, before the break, instrumental variable and all these things like more that more dealt with causality, but not causality, why does thing happens, why outcome happens. So now in session 2 we have already started forecasting, causal inference and prediction, and we have seen that why the forecasting is necessary and what are the application of this and what are the research question can be addressed with the forecasting. And the key idea behind the forecasting was that forecasting always uses the historical pattern to make it informed prediction or informed decision, we can say, about the future. And it's extremely useful in today's field, especially in business sales forecasting, because business needs to know or prepare beforehand, public sector or the research, in research as well. So for this, as we said, we are already using the same data set, airline passenger data set, and we have seen the data set that this data set includes the monthly airline passengers counts, and there are 144 observations from 1949 to 1960. And we declared the data. We have to declare the data set as the time series data set. And we also, before setting any forecasting model, we have explored the data set with the visualization that gives us very important findings about our data set, that it shows upward trend, and it also shows a strong seasonal pattern. That means in some months it reaches to peak, some months it goes down or reaches to trough. This, and also the variability increases over time. We can see the fluctuation here and fluctuation here. There is a huge difference. So that gives us an idea that we also see that non-stationary behavior. So this pattern suggests that raw materials are unlikely to be stationary and may require transformation before ARIMA models we have done until this. We were here, I think, that I explained what is ARIMA stand for. So it's nothing but autoregressive integrated moving average. So it has three components. The first AR is autoregressive, that nothing but that's current value depends on the past values. And I stands for integrated or differencing, removes trend and helps achieve stationary. And MA stands for moving average, that's nothing but current values depending on the past forecast. We also seen that ARIMA, to set the ARIMA model, we need to define three parameters here. Those parameters are called P. The first one is P, and the next one is D, and the last one is Q. Sorry. So what is the first one, or the P stands for autoregressive term. The second one is the differencing, and the third one is the moving average term. In our case, in our example that we are going to do now, I put 111 for our data set. So that means the one autoregressive term and fast differencing. One differencing means the fast differencing, and the last is one moving average term. So here the key idea that we need to keep in mind that ARIMA combines persistence, then differencing and error correction to forecast the future values. So let's we are in this slide, I think. Let's move to the next one. Now, before again moving further, we mentioned that before fitting an AROMA model, we need to determine whether the time series is stationary, and then obviously we would be thinking that what is stationary? Stationary is a series that has statistical properties and remain relatively stable over time, including its mean, variance, and correlation structure. And this is important. Why does that matter? This is important because the most forecasting models assume that the underlying process is stable. If the series exhibits strong trend or changing pattern over time, the model may produce unreliable forecast. So using our airline data, the airline passengers data, we are using appears to show an upward, that already I explained in this, that it shows upward trend and recurring patterns, suggesting that it may not be stationary, but we are going to check in the further steps. One common solution is differencing. Here, how we do the difference, the common solution, that we subtract the current year from the past year. So where we examine the changes one period to the next rather than the original levels of the series. In this process, this process is represented by the integrated common ARIMA, which is I in the ARIMA. So In airline example, the airline passenger series exhibits the trend, seasonality, and non-stationarity. Therefore, differencing may be necessary before fitting an aroma model. So let's move to the next one. I think before going for break, I was up to that slide number 6. Now we're moving to the next slide. So after the visual inspection, we suspected that the series might not be stationary because it showed a clear upward trend and strong seasonality. We now formally test this by using augmented decay Fuller or ADF test, okay, with this command. So already I don't want to go for these two steps because already we have uploaded our data and we have loaded our data, and also we have declared that our data set is a time series data set. So now you can directly copy this and yeah. So let's see what they say. Now we formally test using this augmented decay Fuller or ADF test. The null hypothesis here is of the ADF test is that the series contains unit roots. In other words, the series is not stationary. The alternative hypothesis is that the series is stationary. So now let's examine our test statistics. So here our test statistics is minus 1.748, and at 5% at significance level, the critical value is minus 2.887. So as this value test statistics is not more than uh, not more negative than minus 2.887, we fail to reject the null hypothesis. Then what we can conclude from there? We from this one we can arrive at the same conclusion using the p-value also, that the yeah, that the p-value here you can look 0.4065, which is much larger than 0.05. So therefore there is insufficient evidence to conclude that the series is stationary. So here we can conclude this way that the airline passenger series is non-stationary. So we should difference the series before fitting ARIMA model again. Now, I just wanted to see if there is any question. No. Okay, thanks. So now a difference is making a series stationary. So since our ADF testing indicate that our airline passenger series non-stationary and we need to transform the data. And a common approach is the first differencing, where we subtract the previous observation from the current observation. Uh, and why do we need to do this differencing? Because it will help us to remove the trend, it will stabilize the mean and reduce the persistence and create stationary series. For our airline passenger example, one round of differences we're considering here is sufficient, so we use d equals 1. So the second parameter in aroma, so aroma model is 1, difference is 1. After differencing, the series becomes more suitable for the aroma modeling. So far Okay, now we can move the next one. Uh, Here, after confirming that the series is non-stationary, we estimate the ARIMA with the parameter 111 model. So again, I would say that this two part is done already, so you don't need to run that, but you can run the ARIMA model only. And we can explore that. What does that tell us about? Okay. So the model includes one autoregressive term here, the one autoregressive term, and one differencing term, that means the first difference, and one moving average term. And now we're going to see the estimating result. What is the first one? Um, yeah. So the first one is AR1 is 0.74, which is statistically significant. We can look at the p-value here, and that indicates that strong persistence over time. And then we are also looking at moving average one. uh, it is negative and 0.999. It's almost one, we can approximate, and but it's not statistical significant. You can see the p-value 0.999. So not statistically significant, and alternative specification may be explored. Okay, so here the final take away from this model, that ARIMA model here captures the persistence in airline passenger demand, but may not fully explain all the time series dynamics. So this highlights an important principle in forecasting, that estimation is only the first step. The model diagnoses are equally important. So let's move to the next slide. I can see some question. Yeah, already I addressed these questions, and I can do that because it's not possible to determine, and that's most important factor, that how to determine these things. It requires a lot of um, uh, theoretical background to see, because we cannot be sure about these things. But I will give you some tips that how can we address these things later as we move on. Okay, now evaluating ARIMA model diagnostics here. So after estimating the ARIMA model, we should always examine the residuals. So this is one of the things that we need to consider before finalizing our model. So here, if we ideally, residuals should behave like white noise, meaning that random and contain no remaining pattern. From the residual plots here, we can see that residual do not appear completely random, and their variability increases over time. So let's run these codes and see what our output said, and then we go for explanation. Sorry. We have this one, I already have included. So another thing I have to say here. Okay, so as I have the visualization here, I would like to keep on my stata slide, the test statistics. So Here, what the residual plot say us that residual variability increases over time. Residual do not appear completely random. Some patterns remain, suggesting the more model may not fully capture, suggesting the model may not capture fully the series dynamics, and future diagnostics are required. So we need more diagnosis. But now we have run this test statistics, and it shows the Leon box test, the test statistics is 502.71, and at the p-value is 0. That reject the white noise hypothesis. So what we can conclude from here, that residual do not appears to be purely random, and the test statistics strongly reject the white noise assumption at which is statistically significant, and ARIMA does not fully capture the time series structures. Forecasting model should be validated and refined iteratively. So this illustrates is an important principle in forecasting. Model estimating is only beginning, and diagnostic and model refinement are equally important steps in building the reliable forecast. So we are just, as I said, that estimation doesn't really confirm your model choice. So you have to do the model refinement based on those estimatics and the diagnostics. Now we move here. The possible, how can we improve our forecasting model? That some of you are asking even question that how can we know that how to choose the parameters. Okay, so there is no one hard and fast rule that okay, follow this and this, but you need to refine your models. So forecasting is rarely one step exercise, remember, and we usually examine an initial model, examine its diagnostics, and then refine the specification if necessary. Okay, so because ARIMA 111 model still showed the residual autocorrelation and failed to reproduce the historical pattern well, we should consider alternative models. Okay, so since the airline passenger data exhibits a strong yearly seasonality, a seasonal ARIMA model may be more appropriate. I think someone was asking about that, and I replied already that what should be appropriate model for that carbon emission. So you can focus on this model is ARIMA that take care of the seasonal variability. Okay, so here, since the airline already. In practice, we compare several candidate models using information criteria such as AIC, BIC. We also examine the residual diagnostic and then choose the model that produces realistic forecast and approximately white noise residuals. So in while model specification, you need to keep the principles in mind. Selecting a model, that a forecasting model should produce approximately white noise residuals, capture the trend and seasonality, and have relatively lower AIC or BIC values, and that generate realistic forecast. So again, it's important to note here that forecasting is an iterative process. So you do the estimate, you do the diagnose, you refine your estimate or model, and then you go for the forecasting. Okay, now when we are moving to that forecasting future passenger demand, here, so now we use our estimated model to generate forecast. After adding 12-year period. You can see here, I'm adding the 12 months period, I think, 12 future period. We compared the forecast with the historical passenger series, and actual data displays strong upward trend that we have seen clearly clear yearly seasonality that also we have seen, and increasing variability. In contrast, the forecasting remain close to zero. So let's see with this commands for the example forecasting to explore what does it say us. Okay. When we look at this graph, I didn't include here because my slides are, I think, over flooded with a lot of explanations. Though it's not very good in the PowerPoint to see so many text, but at the same time, as it's a crash program and it's a very short time program, so I try to be as detailed, include as detailed information as possible, so that in case you miss something during the explanation or you did not understand, you can read them and get a better idea. So when we look at this one, what we see that at a 12-year period and generated dynamic forecast, compared the forecast with historical. What do we observe in this? Historical passenger data exhibit upward trend. Yes, this is the historical one, and strong yearly seasonality that we also seen before, because the same one I showed you before, and increasing variability. However, the forecasting, this is our predicted one, it remains close to zero. It's not showing or capturing that variability, and it do not produce the observed trend, and it do not capture the seasonality. So here the diagnostic also confirmed before, because in the previous slide you have seen the diagnostic statistics that shows that residual are not white noise. So in principle, what we would like to conclude again from the last slide, that forecasting is an iterative process where we need to keep on refining our estimation, diagnose, and then model. We need to keep on refining our models, and then we can say that forecasting can be to some extent valid. So also another caution here, that never rely on forecast from the model that falls that fails the diagnostic set. So it requires refinement. So yeah. Now to address those things, as I said, that forecast, when you are dealing with forecasting, you need to continuously refine your model. If it fails the diagnostic, then you need to consider other estimator. So one can be difference in differences, and what does it mean that? Many policies happen over time, such as minimum wage increases, education reforms, and the public health intervention, for example. So suppose a job training program is introduced in one region but not in another. So if the employment increases afterward, we still do not know whether the increase are caused by the program, uh, job training program, or by other factors such as economic growth, inflation, or changes in the business cycle. So to deal with this kind of thing, difference in difference solve this problem by comparing the changes over time in a treated group. In our case here, maybe people who were in the job training, as relative to the control group, that means people who did not take part in the training program, that help us actually isolate the causal difference in the intervention. So Uh, Here, what we can say, why not simply compare before and after? The problem is the employment may change because of the economic condition. Already I explained all these things here. So the key idea here is difference in differences estimate the causal effect of an intervention by comparing changes over time between a treated group and a controlled group. So we are going to have two groups. Now, to have a better picture or understanding of the difference in differences, the basic setup, if we consider this table here, before and after comparison. So if our control group before the policy was 70 and then after policy it improved by 5, that means 70, that means changes plus 5. And with a targeted group or treatment group that people in our example, for example, has taken part in the job training program. So from the before policy, the employed number was maybe 65 and now became 85. So here 20. So we can see clearly that the treatment group's change is much higher, but also in the control group there is a change, though it's low, but there is a change. So after counting the we only looked the treated group, we might if we only looked at the treatment group, we might conclude that the policy increased the outcome by 20 units. But the control group also improved by 5 units, as we said, suggesting that some of the increase may have occurred even without the policy. It can be that network or I don't know, or something else. So here, difference in differences, remove these common changes by subtracting the controlled groups increase from the treated groups increase. So here we can see that for the treatment group, the change was 20, and for the control group, change was 5. So what we do in differences, we subtract these changes from 25, and then our difference in difference estimate becomes 15. And so in other words, after accounting for general trend affecting both groups, we estimate that the policy increased the outcome by additional 15, not the 20. We cannot go direct conclusion that for the policy intervention, the number of employment has increased by 20, but we will also take care of the natural or some other factors that contributed to growth by change 5. So here the by 15. So now we move to the next one. Again, difference in difference regression model. How, what's the mechanism behind it again? So here the regression version of difference in difference simply formalizes the manual calculation we just performed. Mm, in the regression, because in the previous one I showed a very simple data set that just to show you visually and understand the concept, but when we deal with the big data set in the real life situation, it's much more complex that we cannot see visually, so which will be taken care of by the regression modeling. So here, all this all explanations or interpretation of the coefficients in our regression model, where beta 0 is the control group's average outcome before the treatment, and beta 1 is the baseline difference between the groups. Beta 2 shows the common time effect. And beta 3 here is the most important one, did estimate, or the interaction term here, treat and the post. So that's the most our important things here, measures the estimated causal effect of the intervention. So let's go beyond the theory and check what happens to our model in the real life scenario. The same example that I have given in the table can be shown in this visualization here. This here, the graph illustrates the intuition behind the difference in differences. Both the group, this is our control group, and this is our treated group. The treated group before and treated group after. Both the group improve before time, but the treated group, this is the treated group, improves much more after the policy intervention. And the additional improvement beyond what we observe in the control group is estimated treatment effect, which is 15. Already, I explained that before. However, this interpretation relies on the empirical assumptions, which is known as parallel trend assumption. What is the parallel trend assumption? Then, where we see, and that, sorry, there is a spelling mistake here, where we assume that the absence of intervention, both the groups would have followed similar trajectory over time. If this assumption does not hold, our did or difference in differences regression estimate may be biased. So now moving to the next one again. The most important assumption is the parallel trend assumption that already I said. We would like to explain that or try to understand that in a bit more to understand the mechanism behind it. So we assume that without intervention, both group would have evolved similarly over time. And the control group approximates what would be happened to the targeted group had intervention never occurred. So since we never observed this counterfactual directly, I mean we can't see it, we use the control group as an approximation of what would have happened to the treated group in the absence of treatment. Because of this assumption cannot be tested perfectly, it's not possible. Researcher typically justifies it using theory and pre-treatment data. So if the assumption fails, that did or difference in difference estimate may be biased again. So again, it's a causal inference. So you cannot address everything here. So next one, how we are going to implement this difference in differences in Stata. So I'm sure that after all this theory, you must be interested to see the output in the Stata, because in this very short session, there are lots of advanced topics coming, and it's hard to concentrate on that. But let's see some figures, facts and figures. What does it show us? So, keeping the research question, did WIS involve differently for the union and non-union workers in 1978? We are using here this data set that we used before. We define this treatment group as union workers and create post variable equal for the 1 year. We have changed here the data set because our line data set cannot be appropriate for showing this. We don't have enough information there. So we are using here that national longitudinal data set for the women work, I guess. Here we define the treatment group as union. So let us see the data set, because I have changed so many data set. I forgot what this data set include. So if I make it describe, we can see the ID code birth and what it includes. The data set is National Longitudinal Survey of Young Women aged 14 to 24 years of old in 1968. Okay. So here, in this data set, what we are doing, the key part of this the model we are going to set here is we are going to define the treatment group as union worker and create a post variable equal to 5 years after 1978. So here we are going to create two groups, control group and um, um, treatment group. That means people who have participated in union and who did not. So after that, we are going to set that difference in difference model. Okay, this automatically estimate the difference in difference effect. So what theory I was showing in the last 3-4 slides, a stata can do within one command only. So you don't need to write so many things. Here also the variables here you can check. So what we can see in our example, the interaction coefficient is negative. So let's look at the coefficient here. This is our difference in difference estimator. This coefficient is negative and statistically significant, suggesting that the union workers experienced lower wage growth relative to the non-union workers after 1978. So most importantly, this coefficient has a causal interpretation only if the parallel trends assumption is satisfied or credible. So now we are moving to another things called lasso. And why lasso then? Why do we need lasso? Modern dataset often contain many potential predictors. For example, wages may depend on the age, education, tenure, um, tenure, then union status, race, and so on. So for wages, we may observe age, education, tenure, union status, region, race, occupation, and many other characteristics, including every variable is not always beneficial because it may lead to overfitting and unstable estimates, and also the poor prediction of new data. So here the goal with the lasso is uh, so lasso here, what is going to do is addresses this problem by automatically selecting the important predictors and shrinking less important coefficient towards zero, improves the prediction accuracy and produces simpler models. So what is the key idea behind this lasso? Is some variables contributes little to the prediction and lasso automatically shrinks or removes these variables. So the goal is achieve a good prediction with the simpler model. So that's our target. So let's check here that how the lasso works in Stata and what we can do here. So in if we consider our research question here, that which variable are most useful for predicting wages, here we use status inbuilt lasso command to predict the log wages using 6 candidate predictors. What are the 6 candidate predictors here? Lasso uses tenfold cross validation and to determine how much regularization is needed. In this 6 example, all 6 predictors are estimated, and meaning each variable contributed useful information of the prediction. So let's run this for this data set lasso command and check that in which way it helps us to predict or do the forecasting. Okay, so the out of sample R squared is about 0.32. Was second 0.324. I don't know. I'm sorry, it's a very long table. Tenfold. Okay, I'll go one by one with you. Tenfold cross validation here, and observation we have 19,005 observation, and also selected predictor is 6. Selected predictors is 6, and out of sample R square, I don't know whether I have included the wrong okay, here I'm sorry, number of observation we can see here 19,005, and then number of covariates or candidates prediction is 6 selected prediction. And now we can see here that out of sample R square is 0.3240. What does that mean? So the model explains around 1/3 of the variation of the wages in the data. And the key point is that the lasso is primarily a prediction tool, and it tells us which variable help predict wages, but it does not necessarily establish the causal relationship. So lasso is designed for prediction rather than the causal inference. So prediction is not the causation, it's just informed decision. And this is the last session, and then I will be taking your question. If you have question, you can write in the chat to save time, because after explanation we'll be having still 10-15 minutes, 10 minutes hopefully, that I can explain, I can give explanation for your question. I can see there are some question in this, and that we will be coming. I'll answer your question one by one soon. So you can keep writing the questions, whatever come in your mind, because I was super tense that I will not be able to answer, I mean, finish whatever I was supposed to finish. I'm sorry. Okay. So the last thing, using the prediction of decision support here, that how can predictive model support decision making? Here, example, um, how can the predictive model support the decision making? So throughout this session, we have seen that different econometric and predictive tools to answer different questions. ARIMA helps to forecast the future outcome, such as passenger demand or sale, where difference in difference help us to estimate the causal effects and answer whether the policy or the intervention actually made a difference, or that through this controlled and treatment group and the control group. In practice, decision makers often need both the prediction and causal interest, the causal understanding. So they have to combine both of them. And the prediction tell us what is likely to happen next, while the causal causal inference help us understand why it helps and what intervention may change future outcomes. So together, this method provides valuable evidence for the business policy and research decision. So here I tried to summarize that what is the main purpose from model to decisions. When we talk about ARIMA, it is used for forecast the future outcome, did estimate the causal effects, and LASSO improves the prediction and select the important variables. So the key message here is what is likely to happen, prediction ask, and causal inference ask, why did it happen? And the good decision making often record the both. So we need to combine them both to have good forecasting, or to make the good forecasting, combine both the prediction and the causal things. So that's all, and I'll stop sharing now my slide, and I can take your question. And I think people can stop recording, so we don't need to record anymore. We are done with the session, and then I can one after another take the question. Dana Lupu, I think you have asked me the question. Yeah. How do we choose? Actually, there is no hard and fast rule that how can we choose P, D, and Q. It's an iterative process. You keep on refining. So first you do, it doesn't work, it violates the diagnostic. So then you can then you need to use the judgment and keep on iterative process based on the test, diagnostic test, and those things. Did is simply OLS modeling for a special input data set, right? No, it's not. So we should also check OLS assumption beside the parallel interpretation. Yes, you must. Because at the beginning I showed the limitations of this OLS model and the assumption, and that it cannot capture the variation or the trends that in the time series we have the external factors. So you must see the um, assumptions. When it violates, then we go to the time series, and then we are going to consider this did. Next, for the objective of evaluation and effect of the environment literacy intervention or capture the control condition, which analytical approach would be more appropriate? A simple panel data, fixed or random effect. We have covered actually this fixed and random effect model or difference in difference yesterday. So you can go through those things. Because today our focus is completely different than the fixed effect and random effect model. And I also explained in the slide as well as in my explanations or the notes that when we should do fixed effect model, when you random effect model is more complex than the fixed effect model, and also there is assumption to satisfy. So when this I mean random effect and fixed effect model gives you the similar or very close output, then I would prefer the fixed effect model rather than random effect model. And when our fixed effect model on random effect model cannot capture the variation, then we can move to the difference and difference model. Lasso is, yes, that's true, is the more in machine learning we use it, and it's much more advanced techniques that you can use for the better prediction that will be omitting the unnecessary variables and choosing the important ones or the most contributing or useful ones to make sure that our model is satisfy the parsimony or in nature. That means it's simple, like including a lot of variable can be very complex. So Lasso takes care of that things. The recording of the two says will be circulated after the session. Yes, the recording of the first session and the second session, both the session will be shared with you. So in case, I'm not sure that how expert is going to share with you. Most probably they can send you the link or they can what you say, upload in the folder that I have shared with you. You can check there, and in case you can't get it in a couple of days, then you can send email to expert people. Can we receive the recording of the session? Yes, I just now taken this. Arifa from Expert, she said that recording will be shared with you all, so don't worry. And if you don't find, then let them know. Thank you for the workshop. Thank you all for participating. It was wonderful session. And it was wonderful to have you. Thank you for the presentation. And I don't see any more questions, but only thank you. Please post the link to the drive again. So this is the link where you will find 2 day sessions. Some of you were in maybe first day where we covered some concept intermediate level, and then today was too advanced, but our time was very limited. And as you know that covering these very complex topics within 2.5 hours is really hard. So I tried my best to include as much as possible. Still, if you have question, you can reach me by sending email to expert. Arifa or Jennifer, can you give them the email address of expert so that they can forward their question to a question to expert, and after I get the questions, I definitely will answer you as soon as possible. Yeah, here is the things, info@sciexpert.com. And also at the end of the slide I have included my email address also. So I'm not sure if you have any complex question, you can also reach me to that. So that's all.